What does it really mean for an AI to think? Today, we're diving deep into big O analysis. Scale demands. Predictive efficiency, modern systems handle petabyte datasets and million RPS traffic. Algorithmic inefficiency translates directly to cloud spend and latency. Big O analysis is the mathematical framework for predicting resource growth as input size n increases. It exposes cost and performance ceilings before a single line of code is deployed. In an era where efficiency is a competitive advantage, Big O is an operational imperative. Without it, systems are designed blindly, reacting to scale failures rather than preventing them. Startups burn runway on cloud bills. Enterprises face revenue loss during outages. Predictive efficiency is the new reliability. But here's where it gets interesting: the invisible cliff. Systems fail non-linearly. Linear assumptions collapse under scale. An endpoint tested at 100 requests may function. At 100,000, hidden ON squared, logic triggers quadratic latency spikes. Monitoring dashboards show symptoms timeouts, throttling but not the algorithmic root cause. Traditional load testing validates thresholds, not curves. Without a growth model, production failures are inevitable surprises. Complexity cliffs are unobservable until breached. The result: downtime during peak events, eroded customer trust, and firefighting teams searching for the hot loop. So what's the real problem? Let's talk about intuition fails at scale. Small inputs mask exponential growth. Developers reason with N10. Production demands NN10 fast. Operations that appear constant time in microbenchmarks reveal logarithmic or linear scaling later. Linear extrapolation is dangerously optimistic. The gap between average case expectation and worst case reality widens exponentially with data volume. Complexity must be reasoned, not measured. Only asymptotic analysis captures the true trend. Even experienced engineers misjudge algorithmic impact without formal analysis. Code reviews often miss complexity regressions. This raises a critical question: the growth function. Big O models growth, not runtime. It formalizes the upper bound of an algorithm's resource consumption as a function of input size n. Constants and lower order terms are discarded to expose the dominant scaling factor. This abstraction reveals the inevitable crossover points where one algorithm outperforms another at scale. Big O is a lens for predicting long-term behavior independent of hardware or language. It answers: if users double, will the system slow by 2x, 4x, or grind to a halt? This single insight shapes architecture. Now let's zoom in on complexity classes, a hierarchy of algorithmic efficiency. O1 constant hash lookup, array access O log n, logarithmic binary search O, linear iteration, simple scan O in log n, linearithmic merge sort, heap sort O n squared, quadratic nested loops, naive matrix multiply O's tune exponential recursive subsets, brute force O n. Factorial permutations, each tier orders magnitude more resources at scale. The jump from ON to ON squared defines the line between scalable and broken. These classes are laws, not suggestions. No amount of hardware can rescue an exponential algorithm at scale. Here's something most people overlook: time and space. Complexity is multi-dimensional. Time complexity measures operations. Space complexity measures memory. Real systems trade one for the other. Memoization caches results, space, to avoid recomputation time. A hash map gives O1 access with ON space. A sorted array O log n search with O1 space. Always consider worst case, average case, and amortized cost. Complexity analysis must account for both dimensions to avoid resource saturation. Memory leaks often stem from unaccounted space complexity. Cache thrashing emerges when average case assumptions fail at the tail. Think about this for a second. Analysis workflow. Code to complexity systematically. Identify basic operations. Count iterations, loop depth multiplies, sequential sums. Recursion, depth times width. Drop constants and non-dominant terms. Assign big O class. Nested loops multiply O conquared. Loops with halving yield O log n. Recursion, master theorem guides. Ignore O2 and On. The dominant term determines the class. Example for I in n, On squared. For I in binary search, On log n. Mastering this reduction is fundamental. And this is where things get complex. Data structure choices. Every operation has a complexity signature. Array O1 access, On search, On insert, On delete linked list, On access, On search, O1 insert, O1 delete hash map, O1 access, search insert, delete balance BST, O log n access, search, insert, delete a single On squared. Hotspot in a data pipeline propagates latency to every downstream service. Selecting the right structure is a leverage point for system-wide performance. The ubiquitous hash map delivers O1, average but degrades to On. Under collisions, a complexity trap. Understand the distribution. But here's where it gets interesting. Architectural leverage. Design decisions are complexity bets. Catching turns On lookups into O1. Database indexing converts On scans to O log n seeks. Partitioning horizontal workload keeps per node complexity linear. Message queues decouple producers, flattening spikes. Every architectural pattern has a big O signature. Choose patterns that keep the system on the lower curve. Autoscaling masks On squared, issues temporarily but explodes costs. Architectural complexity reduction is more durable than adding instances. Microservices with On communication patterns can be globally On unquered if not carefully orchestrated. So what's the real problem? Let's talk about economics of scale. Cloud cost is a function of complexity. Consider a service with 1M daily requests. On log n processing, On squared 50,000 out mar. The complexity class determines the cost derivative as usage grows. Big O analysis becomes a financial planning tool. Preventing On squared creep is a margin protection strategy. At scale, algorithmic choices outweigh infrastructure optimization. A startup with exponential growth hitting an O20 algorithm finds itself technically bankrupt. Complexity is a unit economics variable. CFOs should understand Big O as well as engineers. This raises a critical question beyond load testing. Reactive methods miss asymptotic failure. Load tests verify a specific throughput. They do not reveal the shape of the complexity curve. A system passing 10K RPS may double latency at 20K due to hidden On squared loops. Combine load testing with Big O profiling, trace operations, compute empirical complexity, project limits. Know the curve, not just the point. Tools like BigO.io or custom profilers automate empirical complexity measurement by running stepwise load and fitting curves. Shift testing left complexity analysis in PR reviews. Now let's zoom in on verified efficiency. Formal complexity guarantees. Emerging AI code assistants propose Big O annotations. Static analyzers detect complexity regressions in CI. Future contracts include complexity SLAs alongside latency and availability. Efficiency becomes a first-class property, continuously verified. Big O transitions from interview question to operational KPI. Research at DeepMind and MIT explores neural networks that predict algorithm complexity from pseudocode. Verified efficiency becomes a differentiator. Open source projects will carry complexity badges. The path to self optimizing systems begins with provable asymptotic behavior.